Okay, we just left off talking about how big the Amazon was in discharge in thousands of cubic feet per second, which you derive by multiplying the length of the river, the amount of the river that passed by you in 1 second times the width of the river times the depth of the river. It's pretty easy to do. Here are the major drainage basins in Arizona. Depending on how you look at it, we have two. This is the Gila River. The Salt is one of its tributaries, and the Verde is another one of the tributaries. Of course, we have the Olive Fria, Skunk Creek, Cave Creek, and a few others, but these are the major rivers. Arizona has a divide right across here called the Mogollon Rim. Water that falls north of the Mogollon Rim flows into the Little Colorado River, or the Colorado River. Water that flows down here ends up going out the Gila, which really is a tributary of the Colorado. Then the Colorado, well, used to come down here. You'll watch a video on this. It no longer reaches the Gulf of California. We use up all the water first. There are different kinds of drainage patterns that rivers leave behind. Here, you'll notice they almost look like branches of a tree. Take a look. This is a tree. The Greek word for tree, dendro, which we call dendro, or like dendrochronology, creates a dendritic formation, like dendrites, the nerves in your body. Axons and dendrites, remember that from biology? You can also get radial drainage. When you have drainage going away from a center point, you can be sure that there's either a dome mountain or a volcano there. You can have rectangular drainage, which is caused by jointed rocks, or if the things that cause the joints, ridges, are bisected, you can end up with trellis. And we'll see an example of this in a while with the Shenandoah River Valley. Here is an example of the first one, dendritic drainage. A satellite picture, and I can't remember where this is from, but all these streams are flowing into here, dendritic drainage. This is more like a trellis. I forget where I got this picture. It might be in Canada. I steal stuff from all over the place. Here is what would be rectangular drainage. Whoops, if there were much drainage there at all. This is from the shore of Lake Powell, and the joints in the rocks there tend to be parallel. So the water flows parallel along these, creating slot canyons over time. This I just thought I would throw in because it's kind of cool. I like this. New home. Something mini extras, and you have a view of the river. Here is dendritic drainage, but for those of you who are pretty observant, you're going to notice something odd about this picture. This isn't Earth. This is Mars. And if water is what causes these on Earth, we must assume that something liquid, possibly water, did this on Mars. Right now, curiosity is hoping to discover more about that. More dendritic drainage, it can go crazy. And here is the edge of the watershed. Water falling on this side will go to a different river. Water falling on this side will go into the Manu River. Here's dendritic drainage in Kentucky or West Virginia. And you'll notice that there's some kind of scarring or something on the mountain. What is this? This is called mountaintop removal, where miners go in and remove the entire top of the mountain, dump the products into the streams, releasing all kinds of toxins into the streams, so you can have cheap electricity in the form of coal. Here is radial drainage going out from Mount Rainier. This is really kind of cool. All these little dendrites are tributaries leading into the main river. I have no idea why I stuck this picture in here, but it's kind of cool. Diagram of a riverbed. Okay, we can break rivers into different kinds. We can call them young rivers with canyons, mature rivers with terraces, and then eventually they become old rivers. This is one convenient way to classify a river. This is a drawing from a book, but it's not a very good drawing, so let's look at real rivers. This is a young river. Why is it young? It's flowing fast. It is very erosive. It's digging down quickly. If it's in an arid area, it will dig a canyon. If it's in a humid area, it will dig a V-shaped valley because the sides of the canyon will weather away. I have no idea why it's yellow. I would assume from mining drainage, but you never know. Here are some young rivers in Nevada that are creeping back into a plateau. The waters will flow down here, and this valley will widen, and the headwaters will actually extend back into the plateau. If you want to build your house right here, probably not a good idea. Here is the young Niagara River, a little bit older, but it's still eroding. It is cutting in to the rock that's here. Here's a sample diagram, but it's not very good. Typical young rivers have a steep gradient, very few tributaries, they flow quickly, and they erode deeper rather than wider. This is a young river. What a great place to go hiking. You'll notice big boulders. Why? During flood times, these big boulders can actually be moved by the water. This is crazy. You wouldn't expect it in the Mississippi. You don't expect to see one of these rocks go floating down the slow old man river. But in a flood season, in a young river, that can happen. Most of the time, the discharge is a lot less. Also, because of this, you don't see a lot of really fine sediment, what we call fines in here. Mostly big material. Here is a young river. Again, notice the boulders and the fairly steep sides of the valley. This is your typical mature river. It has widened its valley. Most of the mountains are gone by now. And for some reason, people have chosen to live down here. Oh well. This is an old river valley. What happens in this case is that the water is flowing so slowly that it drops its sediment and blocks its own path, creating what are called these things, meanders, named after the Meander Valley in Europe. This is kind of cool. This is stream velocity in centimeters per second. So this is 1 meter per second. That's 10 meters per second. That's a tenth of a meter per second. And here's the type of sediment. The faster it's flowing, the more likely you are to get erosion. The slower it's flowing, the more likely you are to get deposition or the dropping of the material. What drops first? The gravel, and then the sand, and then the silt. Now notice clay stays in suspension even if the water is barely moving. Again, this is like the little particles of chocolate in your chocolate milk. They can stay up there for a long time. If you've ever left chocolate milk on your counter at night and come back, only after a number of hours have the little particles settled down. If you kept stirring your chocolate milk all night, the clay and even some of the silt wouldn't settle to the bottom. Now, question for you. Which one of these channels would allow water to flow most easily? A, B, or C? Correct answer? A. A spherical or round shape is the least friction impinging type of shape. Okay, just another picture of a young river. This is beautiful. Wouldn't you like to be out there having a picnic? Now, in some young rivers, you end up with valleys, and some you end up with slot canyons. Hippie talk. Here's a sample diagram. You end up with really rapid downcutting. Does this stuff really happen in nature, though? Is this just some kind of geologist's dream? No, it really does happen. This is in northern Arizona and southern Utah on the Paria River. The river flows only occasionally. When it does flow, it's incredibly violent. You don't want to be caught in here. If you are caught in here, say goodbye. People die doing this all the time. You have to hike through here very quickly and never do it during flood season. In an area that's more humid, you will have water flowing constantly through here. And if that's the case, the sides of the valley wall will wear down too, not just the bottom. It's the difference between humid and arid areas. Here we go. Arid areas, you tend to get slot canyons. Humid areas, V-shaped valleys. Why are young streams fast? Well, one, they're narrow. Two, they're also steep. They have a really large gradient. Some rivers may be dropping 100 feet in a mile. Doesn't sound like a lot, I know, but try kayaking one of those. Let me know if you survive. On occasion, slides will go into a river and block it. That increases the speed, which is kind of cool because if you have faster speed here, that becomes more erosive. The faster the water, the more it can carry stuff away. So this is kind of self-healing. And on occasion, humans narrow a river by building obstructions, and that will increase the speed. We have to make bridges and such structures very strong to make sure they don't get washed away. Now, what are ways that a river can wear down its bed? Because if you remember back in the earlier pictures, a river really does wear down its bed. I was looking for a picture. Here you go. This bed is being worn down very, well, in geologic terms, rather rapidly. How does it happen? Well, water going along the bed of the river actually lifts things. If you have ever stood outside with your hose and tried to get something off your driveway or shot a stream of water into the soil, you know that water can dig up things. Miners in the old days used to use hydraulic action to wear away mountains to get at the gold. So hydraulic action, you also end up with rolling or saltation, and the riverbed rocks themselves beat on the riverbed. How is the load of a river carried? There are several ways. Some of the materials in the rock are dissolved. That's called the dissolved load. Sodium, magnesium, some other things can be dissolved. If you take some river water and leave it out on your counter overnight, let the water evaporate, you'll see salts left behind. The only way to get that back out is by evaporation. As long as the river is moving, you end up with the suspended load, which usually is silt and clay, very fine particles that you studied back in your sedimentary chapter. Things that move along the bottom include sand, which moves by a bouncing action called saltation, and yet actually makes those sound effects. Just listen to the sand. Stick your head under a water stream and listen. And then if you've ever walked across a rapidly moving stream, you may have felt materials moving across your feet. This is called the bed load, and it rolls and slides. This really does happen in fast-moving streams. Again, you won't see it down at the mouth of the Colorado River or where the Sacramento or Columbia River dump into the ocean. But in fast-moving streams, this happens. So the river can be carried in dissolved load, suspended load, salt and clay. Bed load can be sand and gravel through saltation, rolling, and sliding. Now a comment. How big of things can be rolled along? There is a rock at Phantom Ranch in the bottom of the Grand Canyon, about the size of a two-car garage. It was moved there during a flood, I think in 1963. It hasn't moved since, but that's how big things can be in order to be moved by a river. We'll stop here and pick up part 3 next.